So we're going to retry this example that we did. But here we have that it's a 5-meter radius and a 10-meter height. And the rate is 3 meters cubed per minute, and the depth is 4 meters. And we're going to try again this time using the right formula. So the first thing that we're going to do is we have a oil tank that has the shape of an inverted circular cone. So I'm going to create a circular cone. And with all these cones, whenever we can base it off a triangle, we like to. So we're going to draw that triangle there. This here is a radius of 5 meters, and the overall height is 10 meters. Okay. And now they've also given us that the depth is 4 meters deep. So this is R, and this is H, which equals 4. Okay. And I'm just going to erase this line and try to make it a little bit better. Right? And they're giving us that they're pouring stuff in. The change in volume with respect to time is what they give us. It's 3 meters cubed per minute. And they give us the height. And the current height, they say, is 4. And they're asking for the change in height with respect to change in time. And here, because we have a cone, our volume expression equals pi over 3 r squared h. So here, using this equation, I know I can solve for dh by dt, but there's this r term here. And if I look in this original expression, they never give me what r is. So I have to somehow deal with r. And to deal with r, we're going to create or look at this triangle that we can find right here. We've got this internal triangle here. Okay. And if we write that triangle, we'll notice something interesting. This length is h, whereas this length is 10, and this is r, and this piece is 5. Because we have a similar triangle, h over 10 equals r over 5. So r equals h over 2. Because we're solving for dh by dt, we don't want to replace h with r. We want to replace r with h. Okay. So this is going to give us v equals pi by 3 h by 2 squared times h, which means v equals pi h cubed over 12. And now that I have it as v is an expression of h, now when I derive, I'm going to get an expression for my change in h with respect to time. So dv by dt equals 3 pi r squared over 12 dr, or 3 pi h squared over 12 dh dt, which equals, so dv by t equals pi h squared over 4 dh by dt. And now dh by dt equals 4 over pi h squared times dv by dt. Now I have my dv by dt and I have my h. So I can plug in those values. My change in height with respect to time equals 4 over pi 4 squared times 3, which equals 3 over 4 pi meters per minute. And now we write our concluding sentence. Where'd the text box go? Insert home. Can I just type? Oh, I can just type. So let's type that here. Control. The rate at which the height or as the oil tank is being filled at a rate of 3 meters cubed per minute, the rate at which the height is changing is 3 divided by pi 4 pi meters per minute when the height is 4 meters. And we have our final concluding sentence. Okay. Now we're going to look at our mean value theorem. In the mean value theorem, we have a function's continuous over the interval AB and differentiable over the closed intersection. Then there exists a point C in AB such that f prime of C equals f of B minus f of A over B minus A, which is the same thing as the slope of the secant line connecting a f of A with B f of B. And what's the idea, or what's the visual idea here? If I take a line, okay, and if I take that line, and it's the line that connects the 2 points there, that's this secant line. Okay, so let's take this secant line and we'll copy it and we'll paste it, okay? And now with this secant line, if I move it up right there, it's the tangent line at this point. So it's the same line with the same slope, but for an internal value, we have the same slope. And this is actually much more powerful than we might think it is. But what's the geometric argument here? If I increase my text, at some point between or at some point in AB, there is a tangent line with the same slope as the secant line. And that's the final conclusion. But how do we get there? Well, the argument is very similar to the argument with Rolle's theorem. If the slope is greater than if the slope starts out greater than the slope of the secant line, it must at some point become less than the slope at the secant slope of the secant line. Thus, the slope must at some point equal the slope of the secant. So that's the argument with it going higher first, having a greater slope first. The argument for if it has a shallower slope to start means that at some point it must get a slope greater, because at the end it has to have that slope. And if it is less shallow at the beginning, it will then become more shallow. So it's a very similar argument. So we can actually copy it and paste it. And now we're going to change it slightly to if it starts out less than the slope of the same secant line, at some point the slope becomes greater than the slope of the secant line. Okay. This slope must at some point become equal because it goes from less to greater. So if the slope starts out more, it must become less, so it must equal at some point. If it starts out less, it must become more, so it must equal at some point. And finally, if the slope is neither less nor greater, it is always equal. So similar to the argument with Rolle's theorem, except for now we're thinking of slopes of the tangent lines. If the slope of the tangent line is greater, it has to at some point become less. If the slope is less, it must at some point become greater, which means it will at some point in the middle be equal. We have our mean value theorem. For all these theorems, remember, we really are looking for the visual idea, the visual understanding of what we're allowed to conclude. We're allowed to conclude that at some point in the interior, there will be a point with the same slope, or there will be a point that whose tangent line has the same slope.